Hello. While you guys are enjoying your lunch, my name is Gijun Nam from IBM. I'm serving as Technical Activity Chair of CEDA. Welcome to IEEE CEDA Distinguished Speaker Luncheon at DAC 2018. As you might know, this is one of the flagship activities that CEDA is sponsoring at DAC. Also, we host these distinguished speaker luncheon activity in major conferences, including the DATE conference and also ICCAT. For example, during the DATE conference this year, which was held in March, we had speaker Professor Jelena Vukovic from Stanford University, and she gave a wonderful presentation on the designing and implementation of the photonic circuits in the computing system. And also, we are kind of still in the process of recruiting the interesting speaker for the upcoming ICCAT conference in November. If you have a good idea or if you have a promising speakers, feel free to let me know so that we can include them into our queues for the review process. Okay. So before I introduce our speaker, main speaker today, we have a little surprising event, award ceremony that we are going to perform here. Let me invite Helen Lee to the stage for the award ceremony.
All right, thank you very much, and I'm very honored to representing on behalf of IEEE Technical Committee and Cyber Physical Systems to introduce our technical committees and also present award. So IEEE Technical Committee on Cyber Physical Systems, CPS, is dedicated working on the technical activities related to designs, implementations, and operations of CPS. We tend to address the close interactions and the feedback loops between the cyber components and the physical components. So our TC missions including promoting CPS-related research, organizing journal special issues, conference special sessions. Also, we tend to establish new CPS journals, conferences, workshops, new CPS-related IEEE standards, publishing CPS newsletter, establishing new awards for CPS activities. The 2018 award chair is Professor Jim Modine. We also work hard to promote educational activity related to the CPS area. There are many societies and councils actually supported us, and TC members coming from many councils and societies as well. We also publish CPS newsletters 2 times per year. I particularly want to express my thanks to all the social editors to make the efforts. So now is our awards. First of all, the TCCPS Middle Career Award is to recognize a middle career researcher from either academia or industry who has demonstrated outstanding contributions to the field of cyber physical systems in his or her career development. And this year, the award winner is Professor David Entienza from EPFL for his sustained contributions to the thermal processor design and the medical wearables. Okay. All right. We also like to award the junior researchers made significant contribution to the CPS community as well. We have 2 early career award winners. The first one is Professor Muhammad Al-Farouk from University of California at Irvine. The award is for his outstanding contributions to energy efficient and security aware design automation methodologies of cyber physical systems. Professor Rajiv Ranjan from Newcastle University is the second winner for his resource and data management models and methods in large-scale cyber-physical systems. We also call for nominations for Technical Achievement Award, Distinguished Leadership Award, Middle Career Award, Early Career Award, and 10-year Retrospective Most Influential Paper Award. There are more details can be found online. And also, if you have any questions or any nominations, please feel free to contact 2019 Award Chair, Professor Xin Li, for suggestions and nominations. Thank you so much.
With that, let me introduce the main speaker of today's event, Professor Gert Cauwenberghs from UC San Diego. Gert is a professor of bioengineering department and co-director of the Institute for Neural Computation at UC San Diego. He received a PhD from Caltech and was a previously professor of electrical engineering and computer engineering at Johns Hopkins University, and also a visiting professor of brain and cognitive science at MIT. His research focuses on neuromorphic engineering, adaptive intelligence systems, neuron, silicon, and brain-machine interfaces, and micro-biomedical instrumentation. Of course, he is an IEEE fellow, and he served many roles for IEEE, including the most recent editor-in-chief of IEEE transaction and biomedical systems. Here's Gert. Please take it over.
So thank you, everyone, for coming. The field of neuromorphic computing actually has been around for quite a while. So if I gave this talk 5 years ago, maybe few of you would have known even the word neuromorphic computing. Today, most of you will have heard it, but perhaps we still don't quite know exactly what the deeper meaning is. So I'll go a bit in that here. So let me first frame this in the context of also some quite remarkable achievement that has been of Google DeepMind recently. Basically, this was almost the defeat of mankind by the machine, right? So we had Google DeepMind, AlphaGo, basically defeating the world champion in the game of Go. This was one of the great open problems in artificial intelligence since the beginning. And if you think of it, right? This was, of course, a very emotional moment for the human, but it was not a fair comparison. If you look at the energy budgets of the machine versus the human, sure enough, yes, the human was defeated, but at what cost? So it was basically 100 kilowatts of power, right, against this about roughly 100 watts, being very generous because the brain consumes much less than that, but basically let's assume the human was there with the entire body, I guess, trying to win the game here. Right, so we have basically 3 orders of magnitude here in power discrepancy. Right, so machine learning and deep learning is great, but there's more to it that in addition to the problem of general artificial intelligence, which we're also trying to get at, right? So this Go is just one particular, very narrow aspect of intelligence. General intelligence is much harder. But then power here also is clearly something that has not yet fully been addressed here. So neuromorphic engineering started about 25 years ago. And as a field that takes inspiration from biology in realizing artificial neural systems that are not only inspired by the function of neural computation, but also by some of the the physical foundations, right, and the primitives, the elements, the physical attributes of what the brain is doing. And this way, by adhering not only to function but also to form and structure and organization, those systems are capable of inheriting also the great energy efficiency and resilience of natural intelligent systems. And very important in all that is also the mechanisms of learning and adaptation, which are key here for then attaining great levels of intelligence. And the roots of this go back to two, I guess, giants, you would say, in the field of computational intelligence or the physics of computation. One being Richard Feynman. In a way, he was foreseeing the great future of information technology by telling us there's lots of room at the bottom, and that really started that predicted a revolution in nanotechnology, which eventually led to the great scaling that we got through Moore's law, right, of transistors, billions of transistors on a single chip. And then you had Carver Mead, also at Caltech, who in a way also had a founding, I guess, contribution to the field by starting really, I would say, computer-aided design, basically design automation, right? Going from assemblies of transistors, right, putting together some function in an ad hoc way, very manual way, into a more automated process, a systematic process, right, in doing modular design. And we owe a lot of that to him, because at least in the initial stages. Now, in fact, Carver actually coined the term Moore's law. He was a good friend of Andy Moore, like I said. But the two also have a great contribution to make in the field of neuromorphic computing. And that is analysis by synthesis. In the words of Feynman, in fact, this is his blackboard just a few days before his passing. He wrote, "What I cannot create, I do not understand." Right? Basically, in order to really understand something, you need to be able to build it. That's the analysis by synthesis methodology, which Carver took to the extreme in founding in the field of neuromorphic computing. So what this is about? So here we have neuroscience is really all about analysis, whereas engineering or neuroengineering is about synthesis, right? And the reason why the analysis approach has been so prevalent is because in order to really get at the function or understand the function of how the brain works, you really need to dive down from the whole brain scale down to, well, as small as you can get in order to really get at a reductionist function, right? And so much of neuroscience has been focusing now at trying to understand how, say, ions move to ion channels, what are the different ion channel types, the receptor types, etc. Mostly at the molecular level. Now, systems neuroscience, right, will then take an engineering perspective in building things back up from the lower scale up to the higher scale in a modular fashion. And doing so, right, as computational systems neuroscience, and we can build models of how the brain works and then validate those models with hypotheses. And neuromorphic engineering has been a means for doing this in a very physical means, right? So Carver Mead realized that the ion transport, right, through ion channels is thermodynamically not too different from how electrons or holes move through channels of transistors. And this thermodynamic analogy actually plays out at different scales in hierarchy as well, including also Boltzmann physics of networks, which also lead then to Boltzmann machines in machine learning. Right? So so this was one realization among many important realizations at the physical level that allowed really, that were at the roots of this field of neuromorphic computing, and that have really then enabled a highly efficient design of circuits emulating that neural functions using this sub-threshold mode of operation of the transistor, where you get many orders of magnitude of dynamic range, right, in current or conductance as a function of voltage. Just the same way, in fact, as you have the scaling of conductance of ion channels with memory potential. Right, and so we started building those interesting devices, ion channels, and then conductances in a physical means. So neuromorphic engineering was really about taking this physical analogs very literally and then implementing circuits that actually really implemented the physics in an innate way. And that gave rise to great efficiency in representations and also really interfacing with the sensory world, with the senses in a very physical manner. Here's an example of silicon retina built by, so this was by Kobena Buanan and his group at UPenn, now at Stanford, right, where you see these different cells, basically, right, so horizontal cells, bipolar cells, American cells, and then those retinal ganglion cells that then convey this information, this analog information from the photoreceptors into then spike-based representations that then project over the optic nerve to the rest of the brain. And so these different cell types are here then coded because in the spike-based behavior of what this chip then produces. And you can actually reproduce the image seen quite well from the spike-based representation, right? So there's something about these representations, the spike-based representations in vision that are really innate and that can really capture the world. In fact, all we see here travels through our optic nerve, right? Just a few 100,000 axonal fibers, right? That each spike about at most 100 hertz, right? So the world that, the visual world enters our brain, right, in a very sparse fashion, right? So sparse both in space as well as in time. So there's actual potential. The spikes have some intrinsic properties that have been exploited for extreme efficiency in representation. Here's another example, our work on a temporal coding imager that takes this one step further, right? And, so basically augmenting then a standard APS active pixel sensor with some additional circuits for threshold detection, change threshold detection, right? So each pixel here responds basically to either an increase or decrease in intensity by a programmable threshold. And you can actually indeed identify what is happening here in the scene. You have a person moving around here. In fact, this temporal code is very useful for surveillance applications because if nothing happens, there's no need to send any spikes, right? Any information, right? So this way, information is innately coded, is represented in the data stream that comes out. Right, so those are examples of neuromorphic or early neuromorphic circuits that do then this temporal coding. Now, in order to get one step further and do cognition, it's important to also, of course, present what is happening in cortex. And here we have the community has embraced this reconfigurable means of implementing large-scale neural systems, right, that emulate then the neural networks with a large number of neurons and synapses that are reconfigurable. And being reconfigurable is important in order for being able to design different networks and not being constrained by what you fabricate at the time of your silicon processing. Right, so the community has been adopting what is called this address event representation, and what it really is simply a means for communicating events from sender neurons to receiver neurons here. So each neuron is given a unique address, and so then information is transmitted over a shared bus, right, where then the data is inherent, right? So the information is inherent in the representation on the bus. Basically, you have events that code on time and space of activity as spike activity is occurring. And one advantage of this event-driven representation is that you can reconfigure then also connectivity purely by changing entries in lookup tables in massive memory. Right? So each neuron in the brain connects to about 10,000 other neurons through 10,000 synapses. And this connectivity is not regular. It has a very wide spread, a very wide spatial range of connectivity, right? Where most connections perhaps are local, but at any distance, there's a fraction of connections that will span beyond that distance. So you need to have a heavy tail in your spatial distribution of connectivity, and then it's important to represent this in an efficient manner. So with lookup tables, you can define for when each neuron fires, you can define in a table what are the postsynaptic addresses where the neuron, where this event connects to, and then you simply pass those events through the network, and then bring it back into your network of neurons. So basically, the way we do it here is we design then neural arrays, so arrays of neurons that are addressable, right? Where you have inputs coming in that are synaptic events, and then you have outputs. When a neuron fires, it sends then an event at the output, right? So with its address. Right? So we call those integrated and fire array transceivers, or IFATs, right? Because you have digital events coming in, asynchronous digital events coming in, and you have asynchronous events coming out, right? As a general purpose system. And the connectivity is then fully defined in the memory around it. Right? So you can get both, in addition to having connectivity that is reconfigurable, this also allows for learning and changing changing connectivities in real time. This modular approach then allows to develop systems in which each module can be separately defined, including modules for vision, such as silicon retinas. So this allows them to construct quite sophisticated models of neural representations in cortex. Here's an example of doing basically saliency-based acuity modulation, basically attentional, basically modeling attention in visual cortex. So, and a very important aspect of all this is also learning and adaptation. And this spike-based representation, this event-driven representation, also allows to implement quite directly biological rules or biological forms of learning as it is observed with actual synapses. And one of those important forms of biological adaptation of synapses, of plasticity, is called spike time independent plasticity, right? In which the strength of a synapse is modulated based on the relative timing from between a presynaptic spike event and a postsynaptic spike event, right? When an incoming spike, a presynaptic spike, causes the neuron to fire a few milliseconds after it, that causal event, right, will then trigger a change in strength that is positive, which makes sense. It's basically a causal event that is a productive event. Whereas a spike that came in too late after the neuron already fired, so when this delta time is negative, a causal event will then trigger a decrease in strength, and eventually that weight would be pruned away, which makes sense because unproductive connections, right, need to be pruned. So that's an interpretation of what this means, but this has been observed experimentally in neurobiology. And those rules can be directly implemented then in this address domain, since you have the lookup tables readily available, where you also have the activity that is presented to it, both pre- and post-synaptic activity. And by keeping cues of past activity, then you can effectively implement those different type of rules, again, in a reconfigurable manner. So those are elements of neural computation and plasticity. Now, how do you put things together and actually build a system that is capable of cognition? So that's where the scaling of task machine complexity comes in. And so here's where also Moore's law comes in, right? So we have the difficulty of a task on the horizontal axis, right? It's basically the performance, what you want to do with your machine. And then you have the cost for doing so on the vertical axis here. Both are on the log scale because clearly there's a vast range of performance or task complexities as well as a machine complexity, right? And Moore's law has taken advantage of the scaling of device technologies, right, to give us exponentially greater complexity that can be accomplished with this exponentially scaling in machine complexity. But once it came to an end, we started realizing that we need to have better trade-offs between those two complexities in order to make progress, right? And so we're now at a stage where really, and part of the reason why deep learning is now becoming so important is because there is little alternatives, right? You can't really push your technology further that much beyond this nanoscale that we're currently at. And it's important to look at architectural considerations for making progress. And so taking inspiration from how the brain works as a gold standard, right? This trade-off between machine complexity and task complexity is quite flat for, all right? Think of it this way. When we sleep or while we're hard at work thinking, our brain dissipates the same roughly 15 watts of power. In fact, when we sleep, even though you would think we're not working, actually the brain is hard at work during sleep, basically consolidating memory, right? Recreating connections. So no matter what the task is being performed, right, we get almost a constant cost of energy, which means for very simple tasks, human brains are very inefficient compared to machines such as, right, for simple tasks such as solving Excel sheets, we would, of course, trust the machine much better than our brains. But for hard tasks, such as, it may not seem hard, but just navigating in cluttered environments, right, so their machines underperform, and so it is important to look at neuromorphic solutions, right? And the solutions here then take advantage of massive parallelism, collective analog computation. Right, so there are two aspects of this. So one is this representation that is allowed by this collective analog computation, but also then deep learning as a means for abstracting from the complex world lower dimensional representations that allow to really get to this better trade-off between machine and task complexity. To quantify this, it's important to look at both, right? So in order to minimize the net cost, energy cost for a given task, in order to get this better trade-offs, it's important to optimize for two things. One is, right, so the energy per operation, and that can be done by greater nanotechnology, right? So better, lower femtojoules, picojoules to femtojoules per synaptic operation or multiply cumulate, whichever way you look at it. And then it's also important to minimize the number of operations per task, right? Together, that gives you energy per task then. And there, we have to look at advances then in algorithms and design of architectures. So we have done this interplay between mostly nanotechnology advances, and then also computer science, cognitive science, neuroscience advances in understanding how the brain does its computation and how to efficiently organize architectures. And so we have all these different disciplines involved here, which makes it great. And so today, in this community, in the design community, you will increasingly have cognitive scientists, computer scientists that have even neuroscience backgrounds that can make advances in the field. In fact, Google DeepMind was founded by neuroscientists that brought that perspective in the field. So let me give, so here's a summary of the current state of the art in large-scale reconfigurable neuromorphic computing. And you'll recognize a few platforms here. For instance, IBM True North is still the largest neuromorphic chip to date, with 1 million neurons and 256 million synapses, minor synapses. This is a digital approach, although it's a asynchronous digital approach, right? So it's quite neuromorphic in the sense that it does take time as an analog variable, even though levels are discrete. So it's a digital implementation. Spinnaker is another digital chip that is more programmable, but less efficient. On the analog side of things, we have the Facets brain scale system from Heidelberg. We also have Cauwenberghs and Neurogrid at Stanford, and our system at UCSD with IFA chips. So the bottom line of the comparison here is that whether you use analog or digital, so the energy efficiencies that can be obtained are now in the order of a few tens of picojoules per multiply accumulator or per synaptic event. And this is orders of magnitude better than today's GPU systems, because mostly the main problem that arises in most of the systems is that the memory is still far away from the processing. And so the cost of computing is actually quite limited, mostly by communicating or getting the bits from memory to the processors. Even though most of those are massively parallel in their processing capabilities, still memory remains a problem. So in order to make progress and go beyond from tens of picojoules in the femtojoule or attojoule range, it'll be important to design more direct interfaces between memory and processing. Another important aspect then of the scaling and going towards larger networks is then this trade-off between flexibility and expandability of your connectivity, right? Since the brain, so the white matter in our cortex, it takes care of long-range connectivity, right? So you have these fiber bundles that connect, say, the two hemispheres, and you also have you can see your spinal cord and all that. So the white matter is important for communication, and the gray matter then does all the computation. There's actually more white matter than gray matter in the brain, just like if you look in any computing system, there's more wiring there than actually there's the gray matter of the transistors doing the work. And so it's important to organize this connectivity very efficiently, right? Ideally, you would like to have great flexibility, that you want every neuron to connect to any other neuron, right? So you want arbitrary connectivity, but you also do want to get a small world system in which you don't want to make too many hops to the network in order to reach your destination. And then tree-based approaches, right? Hierarchical constructs are the more efficient than linear or mesh topologies. So hierarchical address event routing is a means for doing this synaptic connectivity in a highly efficient manner, right? So basically, you partition the network at multiple levels, and in this hierarchy, then you represent at each level your neurons, right? So you include some relay neurons or interface neurons between two levels of representations that just serve the function of passing information between the different levels in hierarchy, right? And the purpose for doing that is because typically when a neuron projects to its other 10,000 destinations, those can be pooled, right? Right, so even though, right, they all have, a large fraction of those have to go far away, you may find that several hundreds of those will end up in the same destination, so you might as well pool those events into a single source event that is being, that goes to your network, right? And this saves wiring and activity in your system quite dramatically. So here's an example then of this hierarchical routing address event system with also IFAT chips, right? Where at the leaf node of your architecture, you have those IFAT chips serving those arrays of neurons with also information on synaptic routing tables. Whereas at the higher level of the hierarchy, so you have the event being routed through your network, right? So when a neuron fires, it sends events locally through all the local destinations, right, in your lookup tables. But then a small fraction of events, of neural events, will be passed up in hierarchy for long-range connectivity to the network. And here we have a hybrid then between analog computing, right, where each neuron here implements two compartments of biophysical membrane dynamics, right? So basically modeling the dendrite of your neuron. Basically the dendrite is what gathers information from other neural inputs. And then the soma is basically the spiking element of the center of your neuron. When it fires, that it sends events along its axon to other destinations. So here we modeled part of the biophysics of the dendritic computation then in analog circuits with conductance-based synapses. And then all the connectivity is then implemented in these lookup tables, right, around this analog fabric. And this chip consumed about 22 picojoule of energy for each synaptic operation. Now, 22 picojoules may seem low, but actually it's still quite high compared with what's happening in the brain. And so it's important to look at different alternative technologies for implementing synaptic connectivity more efficiently. And phase change memory has emerged as one of those modalities for implementing synapses very efficiently. In fact, if you think of what this phase change memory element is doing as a core of this typical now, most of you have heard now of phase change memory. Intel is now coming out with new memory technologies called 3D crosspoint, and you may already have seen optene parts, right, where you have terabits of memory, non-volatile memory, basically as fabrics of crossbar arrays of those elements. And so you have non-volatile storage as well as high data rates of read and write, so very low read and write times in the nanosecond range. So you get the best of both worlds of DRAM and then flash technology in just in one device here. But the same device that can serve as a memory element also serves as an efficient synapse because it really implements a conductance-based synapse, right? When your word line is activated with a presynaptic action potential, this element of this analog weight or conductance, right, represented locally here, will then be activated onto the bit line where those currents can then be integrated. So this implements actually a quite biophysical, this can implement the biophysical synapse with no addition of technology here. Right? So each element, each memory element can be actually a full compute element here in this architecture. And so with Philip Wong at Stanford, as part of an expeditions in computing project with Penn State University, so we developed then these combinations of phase change memory on top of CMOS circuits, right? Where the phase change memory crossbars implement then arrays, basically matrices of weights, whereas then the CMOS underneath implements the neural fabric of this integrated fire transceivers. And then, so the local connections are implemented then in those crossbars, whereas, right, very efficiently, whereas long-range connectivity is still implemented through this in reconfigurable manner through this intergenifier transceiver architectures with hierarchical routing of events. One other important aspect of neural computing is then how do you represent architectures for doing the actual task of say, visual inference. And so here, in addition to getting great benefits of low picojoules per Mach, I guess, energy efficiencies, we're also able, with neuromorphic computing, to accomplish visual or other recognition tasks with fewer operations than what is needed with traditional digital architectures, right? And here also we take inspiration from how biology has organized computation in a reconfigurable manner. The 10 to the 15 synapses that we have in our brain fail about 50% of the time, right? So we have highly stochastic synaptic activity, right? So a presynaptic action potential connecting to postsynaptic destination, that synapse will only be activated with about 50% probability. And you can ask yourself, how can a brain in which all the computing elements fail 50% of the time still be able to actually do useful computation? Well, this is stochastic representation, and stochasticity is not only a source of randomness or noise, but also can serve as a means for doing useful computation. The same way that simulated annealing, right, or Monte Carlo sampling can be used in optimization. Right. So here we harness then this synaptic stochasticity in representations of, in this case, a Boltzmann machine. A Boltzmann machine is a type of neural network that was very fashionable 20 years ago. Jeff Hinton really and Teresinovsky really pioneered and also popularized it. In fact, Boltzmann machines really started the field of deep learning about 10 years ago. Before now, that field has been taking over using backpropagation and using mostly supervised models of learning. But the power of this Boltzmann machines is really, it allows generative learning, which means it can learn probability distributions, even in the absence of labeled data. So this allows for more efficient learning with less supervision than the traditional frameworks for learning. And so here we took a Boltzmann machine, augmented it with this stochastic synapses, and also implemented this, what is called contrasted divergence algorithm for training those Boltzmann machines. Also using this form of spike time independent plasticity. And we're actually able to get greater performance than a digital version of this Boltzmann machine in fewer iterations, right? So neuromorphic computing can also give benefits then of energy efficiency at the algorithmic level. So our latest work is then extending this framework in a hierarchical architecture where HiAER is also implemented on chip with the nodes implementing mostly digital computing, including also learning, all implemented I guess, at the core level. And we just started a new NSF project in which we will make those scaled-up version of HiAER-NSAT, this hierarchical address event routing, neural and synaptic array transceivers available for the community, right? And we're targeting here systems that will eventually have 128 million neurons and 32 billion synapses, right? With reconfigurable learning of biophysical form. So let me slightly shift the gear here. And so far we have looked at general purpose computing, general purpose artificial intelligence implemented with neuromorphic computing in a refigurable manner. But for some applications in IoT, Internet of Things, you may want to go for extreme efficiency, in which you know in advance the type of architecture that you want to design. And then you may want to pass the reconfigurability for greater efficiency in representations. So our earlier work in this field has been developed what we call this support vector machines in silicon, Kerneltron as an adiabatic support vector machine in silicon, in which we have dedicated arrays of processing elements, right? Basically matrix vector multipliers, for implementing the core of kernels in a support vector machine, basically template matching operations, very efficiently. And here we implemented the synapses, these connections between neurons, using charge domain computing. Each element here in this matrix vector multiplier array combines both a DRAM element and a charge coupled device, right? So where the DRAM is then for the storage of your matrix element, and then your charge coupled device implements a non-destructive multiply and accumulate, right, with an incoming bit line, and then you have your locally stored charge that is then capacitively coupled to the output. So this non-destructive operation, right, allows to then operate very efficiently. In addition, we're able to actually recover even the CV squared energy for driving the lines by coupling the capacitive, the charge energy on the chip with an external inductive system, a coil, and then basically recover this electrostatic energy magnetically on the outside at resonance. And recovering basically the energy then adiabatically here in this system operating at resonance at the clock that is tuned towards just right at a constant level of activity. We're able to obtain a teramax per milliwatt energy efficiency. So that's basically a femtojoule, better than a femtojoule per multiply accumulate. Now this was in 2007. In fact, actually the chip was built 4 years earlier, 2003, in 250 nanometer technology, basically 0.25 micron technology. Today, if we're going to a 22 nanometer technology, this would be attajoules per multiply accumulate. To put things in perspective, the synaptic connectivity in the brain operates at about a femtojoule per operation. And the way you can get at this is as follows, right? So our brain, the metabolism of our brain is roughly about 10 watts of power, 15 watts of power. And we have 10 to the 12 neurons, 10 to the 15 synapses. So the neurons fire about 10 times per second on average. So we have basically 10 to the 15 times 10 hertz, basically 10 to the 16 operations per second. And this is at about 10 watts of power. So that gives the energy efficiency is indeed about 10 to the 15, right? Basically operations per watt. So we are already at this nominal level of efficiency if we do this if we organize computation in this very dedicated manner. Of course, you pay a price here because in this case you can really reconfigure your architecture very efficiently, very flexibly, but at least we can get great efficiency in this way. And here's another example that uses, in this case, subthreshold circuits for doing sequence decoding, right? Where then we have another support vector machine, but now in a network with forward decoding for sequence estimation, in this case for biometric verification, that also operate at less than a microwatt of power, which is very appropriate for IoT type of applications that can run even on harvested power. So I gave you examples of systems for both general purpose learning as well as specialized IoT type of adaptive systems. Now, what can you do with this at this interface of biology? In addition to learning from biology, we can also then use those neuromorphic interfaces to actually probe the brain in real time. And so our work also has then been targeting these neuromorphic applications of interface into the brain efficiently and effectively for doing neuromodulation and as a means for non-invasive, unobtrusive remediation of neurological disorders, such as Parkinson's disease. Right? So by building models of basal ganglia and other areas of brain function, then coupled with observing activity of the brain and the body in real time using mobile brain imaging and mobile capture, right? So basically recording EEG, electroencephalogram recording from the brain, as well as EMG, electromyogram recording from muscles, and then motion capture. Then coupling that with models for feedback control, neurofeedback. And the feedback is then in the form of force feedback. So this is a means for them doing non-invasive remediation of Parkinson's disease and other neurological disorders. And so having neuromorphic models is then key here for making this loop more tight and more efficient. Where adaptation occurs at two levels here. The adaptation of the inference, the control system itself, the MIMO, the multiple input, multiple output systems. But also, we can harness then the adaptation, the natural adaptation of the brain itself too, the plasticity of synapses, that by this neurofeedback, they can guide the brain to become more resilient and solve some of its own problems. And so we couple that with also work that we did on this wearable EEG systems, right? Including them for doing real-time imaging of brain activity using then Dry-EEG systems. Right? This is with a spin-off Cognionics, and then also the Schwartz Center for Computation Neuroscience at UCSD, right? Where we can really, through ICA, independent component analysis, right? We can actually really tell what is happening in the brain functionally and with reasonable spatial resolution, centimeters. And so in summary, right, so neuromorphic computing has come a long way, and it is now getting to the stage where it is really coming at the forefront of learning and intelligence. And so techniques that are now being explored for deep learning and artificial intelligence will have even greater advantages or a greater impact once those are combined and with those extreme efficiencies that we can get, that can be afforded by taking direct inspiration from what we learn from brain function. And perhaps even greater advantages will be in the long term where those neuromorphic systems can also interface then with human-computer interaction systems at the pervasive scale. And with that, I'm complete.
With the interest of time, I think we have just time for one quick question, if there is any from the audience.
Subhashis, yes. So, well, make some better memories and have them more efficiently interface with processing. Because the bottom line of all of deep learning, artificial intelligence, is better access and more adaptive operation of those memory technologies.
So memory bandwidth and memory access?
It's a bit different. So we don't care too much about bandwidth, actually. We care more about pervasive, massively parallel access. So each memory element, yes. So bandwidth, not basically the time multiplexing access that you typically have with memory, right? But basically have your compute power directly interfacing with memory. And also, we care more about fine-grained adaptation than we care about, say, precise resilience of multi-level memory. Thank you.
Okay. That was a wonderful talk. He talked about the neuromorphic circuits, also energy efficient system circuits. I don't know which topic is more appropriate for this DAG audience. So let's give one more hand to our speaker here.
Thank you.
And as a small token of appreciation, we have a small plate for you.
Thank you.
All right, that wraps up our session. Thank you very much.